Ever wonder why a compass always points north? Or why magnets stick to your refrigerator, but not to your wooden table? These questions might seem simple, but they lead us to one of the most fascinating aspects of physics: magnetism. To understand magnetism, we first need to delve into the idea of moving charges. You see, in the world of physics, moving charges provide the foundation for understanding a plethora of phenomena, including magnetism. So what exactly is a moving charge? Well, it's just as it sounds. It's an electric charge that's in motion. This could be an electron orbiting an atomic nucleus, or it could be the flow of free electrons in a wire, creating an electric current. Now, remember this: whenever a charge moves, it creates a magnetic field. Picture it like a ripple effect in a calm pond after you've thrown a stone. The moving charge is the stone, and the ripples spreading out are the magnetic field. Now that we understand what moving charges are and how they create magnetic fields, let's visualize this process. Picture an electron rushing through a wire. As it moves, it creates a magnetic field around it, just like ripples spreading out in a pond. The faster the electron moves, the stronger the magnetic field it creates. And if it changes direction, the magnetic field ripples change direction too. Now imagine a whole bunch of electrons, all moving and creating their own magnetic fields. These fields can interact, combine, and even cancel each other out, creating complex patterns of magnetism. It's like a ballet, with every dancer, or electron, moving in sync, each one's motion influencing the others. As you can see, the dance of moving charges is a beautiful and complex ballet, choreographed by the laws of physics. In our previous discussion, we touched upon the fact that the Earth is a giant magnet. But how does this phenomenon occur? Well, the Earth's magnetic field is created by the moving charges within its molten iron core. Let's imagine the Earth as a large bar magnet with magnetic field lines extending from the North Pole to the South Pole. It's these invisible field lines that a compass aligns with, guiding explorers and adventurers for centuries. But it's not just about navigation. The Earth's magnetic field also plays a crucial role in protecting life on our planet. It acts as a protective shield, deflecting harmful solar radiation and preventing it from stripping away our atmosphere. So you see, the Earth's magnetic field is not just a fascinating scientific fact, it's a vital part of our planet's life support system, silently keeping us safe as we go about our lives. Magnetism, then, is simply the force exerted by these magnetic fields. This force can either attract or repel other magnetic objects depending on their orientation. That's why a compass needle always points north. The Earth itself is a giant magnet, and the compass aligns itself with the Earth's magnetic field. But why does a magnet stick to your refrigerator and not your wooden table? This brings us to the concept of magnetic materials. Certain materials like iron or steel contain domains of aligned atoms. When an external magnetic field like a fridge magnet comes near, these domains align themselves with this field, making the material itself magnetic. Wood, on the other hand, is a non-magnetic material. Its atoms are randomly oriented and don't align with an external magnetic field. That's why your magnets won't stick to your wooden table. So, to summarize, moving charges create magnetic fields, and it is these fields that exert the force we know as magnetism. This force can either attract or repel, depending on the orientation of the magnetic fields. And finally, whether or not a material is magnetic depends on whether its atomic structure can align with an external magnetic field. From the simple act of a compass pointing north, to the complex workings of an electric motor, moving charges and magnetism are integral to our understanding of the physical world. So, next time you stick a magnet on your fridge, take a moment to ponder the invisible forces at play.